So in this final subsection of section 0.2, we will be talking about rational exponents and a bit about their properties as well. First, a definition. If a is a real number and n is a positive integer such that the principal nth root of a, that real number, exists, then we can define a to the 1 over n, that's all in the top, as follows. We can define it as the nth root of a. Okay? So this is the same thing as a to the 1 over n. Moreover, if m is a positive integer, then what we can do is we can define a to the m over n. Using this, we can either write it as a to the nth root of a to the m, or, since we know it's the same thing, the nth root of a all to the m. Here, 1 over n and m over m are called rational exponents. They're called rational exponents because they are fractions, and those are rational numbers. So, for example, we now know that any root can actually be written as an exponent. This explains a lot about why radicals and exponents work so well together. Namely, square root of 3, well, since that is really a 2 there, we can write that as 3 to the 1/2 power. Here, we can write this in a similar way as 3xy to the 5/2 power, because that's a 2 there. And similarly still, we can write this as 2x times x to the 3/4 power. However, we can actually, knowing that these are both the same base, we know that multiplication of bases adds the exponent. This really has this is really an x to the 1st power, so we can write this as 2 times x to the 1 plus 3/4. 1 plus 3/4, well, we need a common denominator since we're adding fractions. That would be 2x to the 4 over 4 plus 3/4, which is 2x to the 7 over 4. So now naturally it's time for you to do an example. So go ahead and write all 3 of those expressions in exponential form. So pause the video, and on the count of 3, I will reveal the solutions. 1, 2, 3. So now you can go through and check your solutions. So we're going to go ahead and work a couple more examples still. So for this one, we're going to try to write each expression in radical form. Here, we can write this expression as x squared plus y squared to the 3/2. If we apply the square first, then we get this. Of course, we could also write this as the square root of x squared plus y squared all to the 3rd, and then square rooted. A quick note, the square root, you'll notice if you look at your radical properties, the square root doesn't break up across addition. That's because the square root works well with multiplication and addition because it's some sort of an multiplication and division, because it's some sort of an exponent, as we see here. Exponents work well with multiplication and division. And then we know that multiplication works with addition and subtraction well. For this one, if we go ahead and write this out, what we notice is we can actually bring out a 1/4 times everything, but the 2 has to stay there, and we have y cubed z to the 1st, all to the 1/4. But then that means we could write it as 2 times the 4th root of y cubed times z. So it's pretty neat that you can actually go between these two. Here, negative exponents tell us that that's really 1 over all of that to the positive variant. which is 1 over a cubed, but then the 2 gives us a square root. And here we can write, if you notice that this is x, if you notice that 0.2 is the same thing as 2/10, which is the same thing as 1/5, then we can write this as x to the 1/5, which is the same thing as the 5th root of x. And that looks much nicer than that. So now it's time for you to try an example. So go ahead and try writing each of the following expressions in radical form. I'll reveal the answers on the count of 3. 1, 2, 3. So there are the solutions. All right, one more example. Let's go ahead and simplify each of the following expressions. So we have negative 32 to the negative 4/5 means we actually have negative 32 in the bottom to the 4/5, which means we're actually taking, I'm going to write it this way, negative 32. We can either take the root or apply the exponent first. I'm going to take the root first to make it simpler because that'll be easier to compute the exponent. So if we take the 5th root of 32, then raise it to the 4th power. The 5th root of negative 32 you can calculate to be negative 2. And negative 2 to the 4th is going to give me a 16. So we get 1/16 as our answer. Here, this is just like before, namely negative 5 times the 3. Pull both of those out and then group the x's together. And we have 5/3 x to the negative 3/4. Well, of course, we can put those together, assuming we can calculate that out. So negative 15, those multiply. Then here, the multiplication is x to the 5/3 minus 3/4. Of course, these don't have a common denominator, so we need to get a common denominator. 12 works splendidly, so multiply top and bottom by 4. 20 over 12 minus multiply top and bottom by 3. 9 over 12. 20 minus 9 is 11, so we have negative 15x to the 11 over 12. Here, we can write this as a to the 3/9. And here it's preferable because we recognize that it's a to the 3/9, so we can reduce that fraction. We'll go ahead and reduce that. So reducing the exponent, we end up with 1/3. Here we know that we can actually do multiplication of the two. I'm going to write it a different way though, just so you can see how this works. So instead of using a radical property, I'm going to turn this into exponents and use an exponent property. Because now I recognize that's really 125 to the 1/2 times 1/3, but that's 1/6 to the 1/6. Or if you prefer, this is 125, this is the 6th root of 125. So it sort of depends which one you want. Here, I guess we could also say this is the cube root of a. Okay. And finally, we have this one. Well, again, we notice that these are the same expression in the base, so we can actually add those exponents. They're already a common denominator, so we just subtract them. 4/3 minus 1/3 is 3 over 3, or just 1, actually. So that's just 2x minus 1 as the answer, because 2x minus 1 to the 1st power. And let's have you work one more example. So go ahead and simplify each of the following expressions. On the count of 3, I'll reveal the answer. 1, 2, 3. So now you can go and check your answers. Here are 3 helpful guidelines when reducing and simplifying radical expressions. First, make sure all possible factors are removed. Secondly, make sure all fractions have a radical-free denominator. And finally, make sure the index of each radical is reduced. So these correspond to several examples in the last 3 sections, and these are just 3 helpful things to take away. If you would like some more practice in reducing and calculating with rational expressions, be sure to see pages A23 and A24 of the text and try working numbers 6 and 57 through 68. In our next video, we start our 3rd section, which is all about polynomials.